Uh, so last week we discussed about the message queues, and if I remind about it in a brief, so message queues are created in kernel uh, space, and it could be created by one process. And since the message queue resides in kernel space, any process who is knowing the message queue identifier, which is nothing but an integer value, which is obtained using the function msg message get. Any other process which is knowing this message queue identifier can send and receive messages to this message queue, enabling inter-process communication. So this message queue does reside in the kernel space. So the processors need not to share anything. The only thing which should be known by the process is the message queue identifier, or the, in other terms, the file token used to create the message queue identifier. Right? So if the file token is shared between the processes, then any process can generate the or retrieve the message queue identifier using the file token, and then they can send and receive messages. And the advantage with respect to the pipes is, so not only in first out manner. So as I explained last week, message queues are stored as linked lists in the kernel space, so that using the type of the message queue, it may be retrieved in even in first out, or using the type as required by the process. So to demonstrate the functioning of message queue, so I have created this exercise, right? So in this exercise, so what has been asked is, first there is a process, and then it will create two child processes, C1 and C2, where C1 is a child of the initial process and C2 is the child of C1. That means the initial process creates the child C1, then child C1 will create another child of his. That means C1's child as C2. Therefore, C1 is the parent of C2. The initial process is the parent of C1. The initial process is the ancestor of the process C2. That means parent of parent, right? Uh, so here, so first the process P1 is required to create a message queue and send these messages to the message queue. So I told you that in last week, the message queue structure is something like this. That means it has the message type and the content, the data of the message and the message type. Message type is a long, means a long integer, and the content is an array of characters. That means set of bytes. Content is a set of bytes, and it is grouped or identified using this long value message type, right? So with that in mind, so we have 8 messages. This is the type and this is the content or text. So the parent process must send these messages to the queue, and then the first child process, that is C1. C1 must read the first 3 messages of the queue in first out manner. That means this is the first message sent, second message sent, third message sent. These three must be read by the first child C1, and the C1 should print into the terminal along with the process ID. Along with the process ID, it should print. After that, the first child will wait until the second child reads uh, another 4 messages, but in the ascending order of the type of message. That means the next, so there will be 5 messages remaining in the queue. After the first child reads these 3 messages, there will be 5. Out of those 4 messages should be read in the ascending order of type. That means first this message, then this message, then this message, after that this message should be read in ascending order, increasing order of the type. So at last this message 300 will be remaining in the queue. So after the child C2 reads these four messages, then this will be remaining. Then it should print in the console. It should also print in the console. So I will for you to understand clearly, I will specify which child. First child means C1, and the second child means C2. So the first child process should wait until the child C2 reads next 4 messages in ascending order of this type. After that, the second child, that means C2, will terminate. So after it reads and then it should print. After it reads and print to the console, it will terminate. So after printing the 4 messages, it read. So after it terminate, so the process C1 is waiting until C2 is terminated. So the process C1 read the first 3 messages and then wait until C2 terminates. So C2 terminates after reading the remaining messages in the ascending order. It will terminate. Then the process C1 must also terminate. Child 1 means C1. C1 must also terminate. So after the initial process, so if I say the initial process as P1 must read the message with type 300. That means the remaining message. This will be the remaining message in the queue. And it should terminate after printing the read message with the process ID. So this is the program that we need to create. So last week we covered the theory part or the system calls which are required to use message queues. So we learned basically 4, that is MSG get. MSG get is used to either create a message queue or to obtain the message queue identifier of an already created queue. Right? Then MSG send, message send. That is to send a message to an existing message queue where the message queue identifier is known. And similarly, MSG RCV, message receive, is used to obtain or remove a message from the message queue to a given structure. And at last, the message control, MSGCTL, which can be used for different purposes, but in this lesson, we will be only using it to delete the message queue from the kernel memory, because in even though the processes which refers to the message queue are terminated, the message queue can still reside in the kernel memory. So it should be removed before the process is terminated. right? So MSGCTL, our message control, is we are specifically using it for that purpose. Right, so this is the program that we need to create. So we need to create, first there is a process, they need to create two children, and the parent process must send these messages to the message queue. Then child C1 must read and print the first three messages. Then the child C2 must print the next four messages in ascending order. And the last message remaining should be again read by the parent process. So this is what we need to do. Okay, so we'll go to Linux and program this. Right, so I will create a new directory. So message queues. Now I will create a new C file for that. And I will use gedit to open it. Okay, we will write the program from scratch. So as you know, we need to include a set of header files. So we'll include the header file specifically required for inter-process communication using message queues. So we need to include sys IPC standing for inter-process communication. And then we need to specifically include this msg.h. This is the header file which define many functions which is used in implementing message queues. And not only that, so when we are handling with fork system call also, we need to get sys types.h. And when we are going to create a message queue using msg get, we have a set of flags. In the second argument, we have a set of flags. So if I remind you about that one, so I'm referring to this msg get. So the second argument is msg flag. So what are the message flags which are required? So IPC create, IPC exclusive, and these read, write, execute privileges for users. So those you learned that they are defined in sys stat.h. So in order to include them, you need to include sys stat.h. And as we use system calls like fork is defined in unique std.h. And we should use the printf. So stdio.h should be included. And we will be using functions like exit. So those are defined in stdlib.h. Okay, so if any more additional functions are required, we will include when they are required. So the return type of main is integer, main void. Return 0. Okay. So first, what is required is there is a process. So when this program begins, there is a process. We need to create a child process out of that one. So we will use this type. So PID process IDT is defined in sys types.h. So as we have two processes to create, I will name the first process ID as process ID1 and I will call fork. This will create child1 and initial process. Initial process is already there. So calling this will cause child1 to be, or C1 to be created. So we will switch the operation based on the process ID. So in case the process ID is -1, so make sure that you indent properly. Otherwise, it's difficult to identify when we have multiple hierarchical structure. So case -1, we have the error case, and don't forget the break. And case 0. This is where the C1 comes. C1 comes for the case 0. Right, then the default case. Okay, so I named the initial process as P1. So to quickly identify where we are, which process should be written inside this. So I'm just commenting this one as P1. P1. And here it will be C1. And not only C1, so inside this, we need to create the C2 also. So within this code, you will have the processors C1 and C2. Why? Because the parent, so when you call fork in the initial process, parent will come here, then parent will execute here, and here C1 will come here, then it should create C2 also here. So C1 and C2, if you want to find C1 and C2, you must search within this block, right? Okay, so the child C1 will now again invoke the function fork. So I will use the process, a different process ID, PID2, to distinctly identify the two processes. Process ID 2, and it will create call fork. When it calls fork, similar thing will happen. That means we have to switch again based on the second process ID. So we have to switch inside this one. So it will also have case 0, -1, and default. Case -1. So we have to print the error here. Then case 0. So case 0 is the place where the child C2 comes. So case 0, because 0 is returned for the child. So the child of C1 is C2. So this is the place where child C2 executes. Here is child C2. Then in the default case, this is the exact place where child C1 or the parent of C2 executes. This is child C1. This is the place where child C1 is executing. And don't forget break. So just to make sure that this structure has been correctly written, we'll see whether there is any syntax errors or not. Yes, no syntax errors. That means this structure is okay. So now we have to go to the specific case and write what each of these processes do. So we here there is parent, that means the initial process is here. So P1 I am referring as initial process. Initial process should execute here. Then the child C2 should execute here. Child C1 should execute here. So at these three places, we will write what each and every one of them will do. So not like in pipes, we don't need to create the pipe before calling fork. So in the pipe example, we created the pipe using one process using the pipe system call, and so that pipe was created and two file descriptors were associated with it, and the child processes of those parent process inherited, or in other terms they had their own version of two file descriptors connected to that pipe, own version of file descriptors connected to that pipe. So because of that one, so it is very effective when the pipe is called before the children are created. That means at a place like this, before calling fork, because then automatically the children will get the file descriptors connected with the original pipe. The pipe will not be copied, but the file descriptors connected with pipe will be copied to the children. But we don't need to do something like that here. So we can create a message queue by one process, and any other process which knows the message queue identifier can access it. That means it can send and receive messages. No need to have the file descriptors associated with it. So no file descriptors are used in message queues. So even if the parent creates the message queue after creating the child or children, it does not matter, because the only requirement to access the message queue is the privileges and the message queue identifier, right? So first we'll create the message queue. So last week I explained you a function to get a unique key using a file token, ftoc. So ftoc system call, I think you can remember. So this is what we discussed last week. So as I explained last week, so ftoc will return a key which is unique to this path name or file name, which is nothing but a character pointer, and this project ID. So for a given project ID and given file name, there will be only one key, which this ftalk will guarantee that there will be only one key for a given file name and project ID. So if you know the file name and project ID, then creation of this unique key is nothing using ftalk. So we will create this key. So the type, as you saw, is of key T. So key T that is defined in this systypes.h. Systypes.h has this data type key T. If you don't include this, then you will not be able to use this function. So I will say that key 1. So I declare a key T with name key1, and I will invoke the ftalk function. As the first argument, you can provide a path name for a file or any other string that you like. For example, I'll just use this doc1.text. You may use any string you want, because the only requirement is this should be a character pointer. That means an array of characters. Character pointer means a string. And the second argument should be an integer. So it can go from 1 to 255. I will say any number that I like. Ftalk. So this is the string, and this is the project number, this argument, which is an integer. So this will create a unique key, which is unique with respect to this file name and this project ID. Then using this key, we will create a message queue. So I hope you remember this function msgget. msgget is used to create the message queue. So this is the msgget that we discussed last week. So its return type is integer, and this is the key that we created using ftalk, or you may even use IPC private if you are only interested in creating the queue. And this MSG flag is the one which is important. So if you are using for creation, you can pass IPC create, or if it is only for creation, IPC exclusive. And these are the read-write privileges. Set read privileges for user, set write. So these things we have already discussed. So the third argument can be ORed with this, or else you can pass this argument 0666 along with IPC create. So for this one, that's why I included sysstat.h. So this privilege setting is included in sysstat.h. Okay. So we will try to create the message queue first. So upon success, this will the return type will be the message queue identifier. The return, what will be returned from this will be the message queue identifier. So that this will retrieve the message queue identifier, and upon failure, it will retrieve -1. So that means we have to handle the error. Error handling also we have to do. So first, I will create an integer known as message queue identifier, and using the message get. So this will return a valid message queue identifier if this is successful, otherwise it will return -1. It will return -1. So what will be the arguments? So the first argument of this MSG get, so there are only two arguments. First argument is this key. So I will pass this key as the first argument. Key 1. Then the second argument is a set of flags. So we are using here in this parent for creation. So it is IPC creation and also it is creation only. So IPC exclusively for creation. And I will set read, write, execute privileges for all users, all groups, and all other users. So these things we have discussed. Set read, write, execute privilege for user, or with set read, write, execute privilege for group, set read, write, execute privilege for others. There should be an I. So this is the set of privileges, and this to specify what is the purpose. We are used to create a message queue here. If there is already a message queue with this given key, so then this will return an error. So we will do the error handling. If message queue identifier is equal to -1, we have to print the error. Printf. So we'll use the same format that we had used in previous lessons. We'll say cannot create message queue. And print error. We'll say message queue. The error is related to message queue, then it will print the error. And error number. No, error number. So because of this one, we have to include another header file that we missed. So that is no.h. And then we'll exit. In the error and exit. And also we should specify which one is doing. So there are three processes. We'll say parent. Parent, I specifically say parent P1. And otherwise, so we created the message queue. So otherwise, we have to continue. If the message queue creation is successful, we'll first print a success message. So this parent again. Message created successfully. Right. Then after creation of message queue, so I remind you the question again. So this is already done. That means two children processes were created. the parent process must send the following messages to the queue and wait until the child C1 terminates. So we'll send these messages to the queue. So how to send these messages to the queue? So before sending messages to the queue, we need to create a structure for the message. We need to create a structure for the message because the message is a structure in message queues. In message queues, message is a structure. So I will declare a structure known as MSG. This is the name of my structure MSG. Then I will create or declare the members of this message structure. So as you can remember, so the first member is long and it is called type, long type, and the second member is a string, or in other terms, text, and it should have a size. So for a given message structure, there should be a size. And there is a maximum for this size. So you can refer that maximum and minimum using this command. So I explained how to get this command last week also. So here, so it specifies the size limits for 3 different types of interprocess communication: message queues, shared memory, and semaphores. So we are here on message queues. So it says the maximum size of a message in bytes of a message queue is 8192 bytes. And the maximum size of the queue is 16 kilobytes. See, this is 8 KB. That means the maximum size of a single message. Maximum size of a single message is 8 KB. That means what is the maximum? What is meant by maximum size of single message is this one. So this is the size of a single message. This is the size of a single message. And this can go up to this limit. That means 8 KB, 8192. And the total size of the message queue can go up to this limit. Right, so this is way lower than the limit. So we can safely use this limit without any difficulty. Okay, so we created the message structure. And so when we were learning about the structures, not only creation of the structures is enough. So we need to have a function to initialize a structure. So I will create a function to initialize this message structure. Then it will be very easy. It will be very easy to create a function to initialize this message structure. So I will declare the function with the return type as this type. Struct message is the return type of the function that I'm going to write. And I will name this function as create message. Create message. And what I will be passing as the arguments is nothing but these two. What should be stored in this. So I will pass whatever a long value. I'll say long X. And so this is a character pointer. So I will say character pointer Y. and this is only the declaration. The function will be defined after the main function. So I'll just copy this function declaration, and after the main function, I will start defining this function. So what is the purpose of this function is initialize a message structure. Initialize a message structure. So first, a new message structure will be declared. Struct message. I will say it as new message. So new message is nothing but a variable name given for a structure of type MSG message, and this message structures. So there are only two members, the type and text. So first this member will be initialized. So how to access a member of a structure you already know. So that is by structure name new message dot operator is used if you use the name of the structure. If you use the address, then you have another method. So new message dot, first one is type, is assigned whatever you pass as the first variable, that is x. So x will be assigned to this message structures member type. And the second one is text. So this text is what? If you take this word text alone, it is a character pointer. Character pointer. So character pointer contains a string, an array of characters, an array of characters. So what should be done is what is passed as the character pointer or string in the second argument must be copied. Whatever passed in whatever pointed by this one should be copied to the pointer, to the memory location pointed by text, to the memory location pointed by text. So we have a very good function to copy strings. That means to copy the content of characters or strings to another character pointer. We have a function known as strcpy, string copy function. So, but we to use that, we have to include another header file, include string.h, that is defined in string.h. So what we will be using the function strcpy, string copy, strcpy. So the first argument is the destination. So we need to copy into what? This structure's member text, that is new msg dot text. Text is the second member of this structure. It is a character pointer. So both the arguments of this strcpy function must be character pointers. What will be done is the content of the second character pointer will be copied to the content of the first character pointer. So this is the first character pointer. This is structures, this message structures, second member text. And to this location, the content of this point, this is the character pointer that is passed inside the as the second argument of this create MSG function. So whatever the content of y should be copied and will be copied by strcpy to text of the message structure. So by this step, at the end of this step, the initialization of members of the MSG structure is over. The only thing remaining is to return what is already initialized. So the return type is struct MSG. So we should return this structure, initialize structure. So return new MSG. So what did this structure initialization function or this create MSG did was it created an empty message structure and initialize that empty message structure's members type with X text with whatever the content pointed by Y, and then return the initialized structure. This is what this function does. Okay, so now we created the message structure and defined a function to initialize the message. Okay, so we will create those. So we should do that in parent process. So we will do that in parent process. We will create messages and initialize them. So struct. So we need to create such messages. Struct messages. We'll say messages to send. Oh no, okay, sending messages, because we are going to send those messages. We can use any name. I just use whatever the name that comes to my mind. And I will create not only one, because we have 8. We have 8 messages to send. So I will create 8 message structures. I mean empty 8 message structures as an array. So this will create an empty array of message structures, MSG structures, but they are not still initialized. They are not still initialized. Okay, so first we will store the text to be sent to these messages in a set of strings. So I'll say character MSG1 equal. So I need to specify the size of this character array also. I'll say the size is 20 because I know already the size. So what is the first message? So for us to identify the first and second messages that we said, I have already set this one as first message, second message, third message, like this. So this will be the first message. So there will be such 8 messages. Right, so this will be the second message. And this will be third. And this one fourth. Fifth. This will be 6th, 7th, and 8th. So here are the 8 messages. These are just the text of the 8 messages that we want to send. And I here created an empty message structure array, empty message structure array. And now I want to send this to the message queue. What I want to do is send this to the message queue, right? So before that, we need to initialize these empty messages with this message and the message type. So how to do that is by just invoking the create message. What is create message? It is the, create message. Create message is the function that we use to initialize the message. So what will be coming as? So if I say sending messages 1, what will be specified as sending messages 1? So sending messages is what? It is a structure of MSG which has 2 members, types and text. So we need to call this create MSG, then pass the 2 arguments. What are the 2 arguments? First the type and then the text. So type is 100, first message. So the first argument is 100. The second one is a character pointer to this one, to the text, character pointer to the text. So this message's character pointer is MSG1. MSG1. So this will initialize the first message structure with type 100 and text as MSG1. MSG1 is pointing to this first message. MSG1 is a character pointer to this first message. So likewise, we have to do this one 8 times to initialize all the 8 messages. We cannot use a loop here because the content is different. So here it will be 100, then it will be 200. Likewise, if there was an order, we could have used a loop. Okay. First one is okay. Second one is 200 and second message. So the second one will be here 200 and the second message, the character pointer to the second message is MSG2. And the third one will be 300, third message. So this should be 300 and this should be MSG3. And the next will be 100, 200, 100. This will be 100, 200. And again 100. And here it will need to send the 4th message, 5th message, and 6th message. And there will be 2 more to be initialized. And here the character pointer should also be changed. So sending messages 1 will be the first structure. Oh no, first the array pointer 0 will point to the first structure, then 1 will point to the second structure, likewise. So we should go from 0, 1, 2, 3, 4, 5 until 7. So there are 2 more. So this will be the message structure pointed by the index 6. That means the 7th message structure, and it will be initialized to 200 type and 7th message. MST7 points to 7th message, and this will be 8th message, and the last two values will be 300 and 150. This should be 300 and this should be 150, and this should point to 8th message, and this should, the whatever the should be initialized is the 8th message structure pointed by sending messages 7. So this, by this point, we have created 8 message structures and initialize them with this and this, these text and these types. So what is left to do is to send these to the message queue. To send this to the message queue. So we have already created a message queue. So what is left is to send this. So for sending, we can use to save code in time, we can use a for loop. Why? Because we can access the sending messages using this array indices. Using this array indices, we can access. Okay, so I will write a for loop to send the message. So the array index must change from 0 to 7. For integer I equals 0 to I less than 8 and I plus plus. What I should do here is send each and every message to the message queue. So if I remind you the function msg send, message send. So the return type is integer. So what will be returned is, so it will return 0 on success, and upon failure it will retrieve -1. So the first argument will be the message queue identifier. So we already know because we have created the message queue. And the second one will be a void pointer to the message structure. Void pointer to the message structure. So the second argument will point to the message structure, then to the size of the text of the message. Size of the text of the message. And the last one is a message flag. It will be either 0 or IPC no wait. So I have already explained last week. So if this is IPC no wait, it will not block if the message queue is, so in sending in MSG send, this will block if you have passed the value 0 here. This MSG send will be blocked. That means you will not be allowed to send if the message queue is full. In MSG RCV, message receive, IPC, if you pass 0 here, message receiving will be blocked if you have passed 0 here. If you have passed IPC no wait, MSG RCV will not be blocked even if the message queue is going to be empty. That is the difference between 0 and IPC no wait. So here the size of the text, and here pointer, it should be of void pointer, a void pointer to the message structure, and this is the message queue. So knowing this function, we will be able to write how to send to a message queue. So msg send. As you saw, the first argument is what? The message queue identifier. So we have already retrieved that. It is this MQID, which is returned by MSG get call. In MSG get, that means when you are creating the message queue, you store the return value of this MSG get in message queue identifier. So this can be used as the message queue identifier in reading and writing, or for any other purpose related to message queue. So the message queue ID is the first one. Then the address of the message structure. So first we have to send this one. But as you saw, the data type is void pointer. Void pointer. So we have to cast it to void pointer. We have to cast it to void pointer. So the first pointer will be this one. Sending messages will be the first pointer. Second pointer will be sending messages plus 1. Third point will be sending messages plus 3. So likewise, using this loop index I, we can set which address of the message structure that we are referring to. So if I say this one as sending messages is the pointer to the first message structure, is the first character point, is the first structure pointer to this structure of type MSG, sending messages, and we can index that using I is this loop count. So sending messages plus 0, when it is 0, that means the first message. So when in the second iteration, it will be I will be equal to 1, then it will be sending messages plus 1. Sending messages plus 1 is the address of the second message structure. It will be the address of the second message structure. Okay. And as you saw, the third argument is the size of the text of the message. So we can just use the size of function, size of what? Size of this one, sending messages I dot text. Sending messages I. Sending messages I refers to the ith message structure of this array. Ith message structure of this array. So it is not a pointer, but this is the actual value, actual content of this message structure. So out of that, we will get the text member. So size of this one refers to the size of text of this message structure. And as you saw, the last argument was MSG flag. That is to specify whether we block if the message queue is full. So we will block if the message queue is full. So we will specify IPC no wait. So this will make sure that the message, the corresponding message pointed out by this I, sending messages by plus I, will be sent to the message queue. So the first, this message will be sent. Then when I equal 1, this message will be sent. So likewise, each and every message will be sent to the message queue. And if you want, we can check whether this is successfully sent or not. So when I explain MSG send, I told you that it will return an integer. It will be 0 if it is successful. It will be -1 if it is not successful. So I will store the whatever received by MSG send in variable x, and if x is equal to -1, we should exit. That means there is an error in sending the message to the queue. Then we should exit the program. There is an error. So did I? Yes, I will use the same structure to print the error there also to save time. So if x is equal to -1, so we are still in parent P1, okay. We'll print a message cannot send to message queue. Parent number is this one and exit. Even if even one message cannot be sent, then we will fail the program. So we will exit. Otherwise, so we send, and we should we will only come out of the loop. So this is the loop. We will only come out of the loop if we are successful. If we are not successful, if at least one of the message sending is failed, then the program will be exit. Program will exit. Okay. So we come out of the loop if only if it is successful. So upon success, we'll print a message. So we should acknowledge who we are. Parent P1 should say that all messages were sent to the queue. Messages were sent to queue. Successfully. And after that, what it should do? So we'll see the problem. So now it send all of these messages to the queue, and it is asked to wait until the first child C1 terminates. So wait. So we can use the wait PID function, but the wait PID is defined in syswait.h. So we need to include the header file syswait.h. So after printing the success message, the parent will wait for the particular process ID. What is the process ID? Process ID. So this is parent. The process ID of child is PID1, because for the parent, the process ID of the child is returned. So the parent will be waiting for the process ID of child, which is the process ID of child one, and the status is we pass the arguments null and zero because we are only interested in the termination of the child, not any other status. So after this one, what the parent will do, it will wait until the child C1 terminates. So the child C1 will terminate after the child C2 is terminated. So whatever happens after the child C1 terminates, at last, after the initial process, must read the remaining message with type 300 and terminate after printing the red message with process ID. Okay, after waiting for the child C1, after child C1 is executed, terminated, this should read the remaining message. So how to read a message? For that one, we need to create an empty message structure. So how to create an empty message structure? We should use the message structure, struct msg. I'll give a name that I want. I'll say receiving message. Struct. This is the receiving message. And I will return from this one. I will get the message received and store in this message structure. So if I remind you about the MSG RCV or message received that we discussed last week, so I told you that it is very similar to MSG send except that it has a fourth argument, long MSG type, to retrieve a message using this message type. All other arguments are similar. So the first one is the message queue ID, then the pointer to the message structure, then the size of the text of the message, and at last the MSG flag, which are very similar to the message send. But using this MSG type, we can retrieve in the way we want. I told you that if this MSG type is set to 0, it will read the messages in a first in, first out manner. It will retrieve the messages in a first in, first out manner if this MSG type argument is 0. If it is positive, it will read the exact message with that message type. If it is positive, for example, if this is 200, it will read the message 200, message with message type 200. And the special case, the other case, which is when you pass this as negative long integer, in that case, it will select the messages in the ascending order, less than the absolute value of the argument passed here. For example, if you pass minus 200 as the message type, all the messages with message type less than or equal to 200. 200 is the absolute value of minus 200. All the messages less than or equal to 200 will be retrieved. That is how it works. If you pass a minus value here, all messages with message type less than or equal to the absolute value of this one will be retrieved. That will be like retrieving in the ascending order up to the absolute value specified here. That means all messages will be retrieved in ascending order up to the message type value specified in this point. Okay, so there are three cases. If you pass 0, the message queue will be read in first out manner. If you pass the exact positive value, then that particular message will be retrieved. If you pass the minus value, all the messages in ascending order up to that up to the absolute value of that minus value will be retrieved. So those are the three cases. So in this example, I will demonstrate all these three cases. So as the parent, we are asked to retrieve the message with type 300. So that is less like passing a positive value. So what will be asked to retrieve is, so I will use this one as integer y. Integer y. So what is the return type of this MSTRCV? It will, y will store the number of bytes read if it is successful. Y will be -1 if message receiving or reading from the message queue is unsuccessful. So here we have to call MSGRCV, message received. So the message queue identifier is used to identify the message queue is same, and the address of the structure, message structure is void pointer, address is this one. So this is the structure variable name, address is the, if you give and, it will be the address. And RCV, this will be the address of this structure, because we are reading into this message structure. And the size will be size of this one, size of RCV message dot text. And the fourth argument will be the type of the message. So we are specifically asked to read the message 300 as the parent, with type 300 as the parent. And then at last we have to pass whether we are blocking or not. So I will specify IPC no wait, that is to not block if it is 0 in MSGRCV. Right, okay. So having done this, we can, if you want, we can check for errors also. If y equal -1, we can print a similar thing like this. So still we are in parent P1, so we will say cannot read from message queue, parent P1 and error number and exit. Otherwise, we will say printf read from the parent successfully. Sorry, not from the parent. So this is parent P1 read from queue successfully. And after that, the parent should exit. we'll say that parent exiting, and then parent will exit. So this is what which should be all done by the parent. So just to make sure that nothing is going in the wrong direction, I'll just try to compile this. Okay, compile, that means there is no syntax error. This is the process which should be done by the parent. Parent will create some messages and send to the message queue. If it is successful, if it is not successful, it will exit. If it is successful, it will wait until the child one is terminated. Once the child one is terminated, it will receive the message with type 300 from the message queue, and the parent will exit. And then we should write what will happen to the other children. First, we will write for the child one. So as in a fork call, both the parent and the child can execute at the same time. So we will provide a small time for the parent process to complete sending of messages to the message queue. So until the parent process sends those messages to the create the message queue and send those messages to the message queue, I will suspend the execution of child C1 and C2 also. So you know the function sleep. I will sleep child C1 for some time. Let's say 0.0001 seconds. That means 100 microseconds. First, I will suspend the process. And then, so once it suspends, we assume that the parent has now already created the message queue and written to the message queue successfully. In that case, we need to retrieve or read from the message queue. So before reading, we should obtain the message queue identifier before reading, because this process has no clue about the message queue identifier, because the message queue was created after creating this child. After creating this child, this message queue was created. If this message queue was created before this child process is created, then this child process will inherit this message queue identifier. This child process will inherit. But as this has been created after creating this child has no clue about this message queue. So it should obtain this message queue. So how to obtain this message queue? That is using this file token, ftoke. So in this message queues, it is assumed that the different processes are aware of the file token or the key. It is used to obtain the message queue. For the same key, you have the same message queue. Okay, so I told you that using message msg get, you can not only create, but also you can retrieve the existing message queue. First, you need to generate this key using the same file token, that means same text and same project number. So again, we will create this key. I'll say again key one. So ftoke, you have to specify exactly like this, doc1.text and same project number. Otherwise, it will generate a different key. So using msg get, so integer message queue id. So these are not duplicates because this is a different process, this is a different process. Message queue id. So now this msg get is used to retrieve the message queue identifier only, not to create. So we need to pass key one, and so none of these arguments will be passed. IPC create, not IPC exclusive, none of this. So this second argument will be 0. If you pass 0 as the second argument or the message flag, when the message flag is 0 and this key is not IPC private, if you specify this one as IPC private, then you will not be able to retrieve the message queue identifier. This should not be IPC private. Okay, so this will retrieve the message queue identifier. Then what is the purpose of child process C1? So child process C1 must read the first 3 messages of the queue in first in, first out manner and print to terminal. Read the first 3 messages and print to terminal. That's what the child process C1 must do. So how to read? First, before reading, we have to create an empty message structure. Struct message, I'll say receiving messages, and I will create an array of structures to store 3 messages. This will be creating an empty message structures to store 3 message structures. Then using the message receive, I will read. So I will store the return value in X, msg receive RCV. So the first argument is message queue ID. The second argument, okay, so this one also, it will be efficient if I do this one in a loop. For integer I equals 0, and this time there will be only 3 messages to receive. That means loop counter should vary from 0 to 2. That means I less than 3, I plus plus. So we will do this in a loop, then it will be efficient. So what the first thing, that means the first pointer to the message structure will be RCV messages plus I, just like we send, but it should be a void pointer. Void pointer. The first pointer is RCV messages. Second pointer will be RCV messages plus 1. Third pointer will be RCV messages plus 2. So this I will decide the message structure message point. RCV messages plus I. That is the pointer or the address of the message structure. Then the size of text inside these messages. So it will be size of RCV messages. So I will run from 0 to 2. So it will be exactly same. RCV messages I dot text. When I is equal, it will be RCV messages 0 dot text. It will extract the size of that one. And then the fourth argument is the type. Fourth argument is type. So we are asked to read in first out manner. So I told you to read in first out manner. the type specifier of MSG RCV must be 0 to read in first out manner, right? Like in a pipe. So this reading is equivalent to a pipe. What was written first will be retrieved first in, first out. And the last is whether we block or not. So to specify that we are not blocking, so we say IPC no wait. IPC no wait. Right. Okay, so that is, so this loop will ensure that 3 messages will be read in order that it was sent. So the first 3 messages, because we have specified 0. The first 3 messages in the queue will be retrieved and stored in this array. And if an error occurs, we will print and exit. So even if one is failed, we will consider the program is failed. So if x equal -1, so I'll just copy the same type of message that we wrote earlier to save time. So if x is equal to -1, that means if any of this message is not able to be received, it will say now it is not parent, it is child. We are in C1. C1 cannot read from message queue. Read from message queue. Message queue. This is child again C1. Print error number and exit. And when it is successful, it will not go into here and exit. It will come out of this loop if it is successful. If it is successful, it will come out of this loop. Otherwise, it will never come out. So if it is successful, we will print red. So first we have to print the new line and child C1. This is child C1, and it will print red from queue successfully. Read from queue successfully. And we are asked to print whatever the messages which was read by the process to the console. So we will print child again C1. The red messages are we will print the messages. And also we are asked to print the process ID also. So to get the process ID, we can use the get process ID function, and it is an integer. With process ID, I will say this one. The red messages are, there are 3 messages, sent S. Now we have to pass the arguments. So the first one will be get process ID, get PID. Get PID retrieves the process ID of the calling function. So it will be printed here. And the second one, and this one, this is the message one. This should be message 1. And we'll say this is respectively in order of reading, respectively. And the second one should be as if it is respectively. So what was read first is this one to the RCV messages 0. So this will be RCV messages 0, not the structure itself, but out of that we should read the text member. That is the member which is storing the string. So RCV messages dot text, first one, and this will be the second one, RCV messages 1 dot text, because it is stored. It is stored here. RCV messages 0, RCV messages plus 1, RCV messages plus 2. So it will correspond to RCV messages 0, 1, 2. Not the structure, but the member, text member. Comma RCV messages 2 dot text. And after that, what the child C1 should do is, so it read from the queue, and then it should wait until its child terminates. So what is its child? Its child is C2. The process ID of C1's child, that is C2, the process ID of C2 is PID2. That is returned in child C1. Child C1 has PID2 because PID2 is returned in this default section. That is child C1. So where are we writing here? Here is child C1. So now by this moment, it should wait for the process ID of its child. That means until child C2 terminates. So this is reading from the queue and print and wait until child C2 terminates. This will wait until child C2 terminates. Then we'll printf child still C1 exiting. That means the C1 is exiting after this one. After the child C1 exits, C1 also should exit. Exiting. Then C1 will exit. Then child C1 will exit. So after this C1 is exit, the parent is waiting until child C1 is exit. After that done, the parent will receive the message with type 300 and print it and exit. Okay. We have forgotten to print what has been retrieved here also. Read from queue successfully. Okay, then we have to print what is read. Okay, we'll print here. So parent P1 message read. There's only one message, no? So message read is okay. We have to print the process ID also with process ID %d. Here we have to use get process ID. And what was read was stored in this message struct RCV message. So we need to inspect this one's text mem. Read message is %. string. So this is RCV message dot text. RCV message dot text. Okay. So now the child C1 and P1 are okay, finished. So what is left to do is child C2. Child C2. So we will even have a longer delay for child C2, because after this one, after child C1, this child C2 should execute. We should wait until even child C1 has finished reading from the queue. So we will add even a more delay to child C2. We'll say 0.01. Means 10 milliseconds. Is suspended for even higher amount of time. After that, we should do the same thing, almost a similar thing which we did for the child one. So first we need to retrieve the message queue identifier of the message queue. Key T, I'll say key 1 is equal to file token fdoc doc 1 dot text, and I have to specify the same argument, otherwise a different queue, a different key will be created here. So using this key, we will use it to retrieve the message queue identifier. MSG get, message get. So first argument is this key, and the second argument is 0, because we are only using this for retrieving the message queue identifier, not used for creation. Okay, so once we extract this one, then so what is the function of the child C2? Child C2 will read the remaining, the next 4 messages in ascending order of type of message. First, the child C1 read these first 3 messages. After that, remaining are these. So out of these, the messages must be read in ascending order of type. So order of type, we can specify. So if we say the highest value here is 300, if we say minus 300, the messages will be retrieved in ascending order less than 300, because minus 300, absolute value of minus 300 is plus 300. Then the queue will be retrieved in ascending order up to 300. So that means 100, then again 100, 150, 200. That will be the retrieving order. Okay, before receiving, we need to create empty message structure array. So struct of message type, I'll say receiving messages. Receiving messages. This structure, message structure array size is now 4, because it needs to store 4 message structures, and we are not initializing them. And using the MSC RCV, we will be going to retrieve this one. So again, I will use a for loop for message receiving to save time and to reduce the length of code. Integer I is equal to 0. Now we have to read the 4 messages. So I less than 3, 4. So it will be 0, 1, 2, 3. and I plus plus. Just like before, I'll declare an integer and use that as the return type of MSG RCV, message received. Message received first argument is message queue identifier. The second argument is the pointer to the message structure. So it should be casted to void pointer to message structure. So message structure pointer is RCV messages plus I. RCV messages plus I. Or in other words, you can also pass this one as RCV messages I, its address. Address of RCV messages ith structures address. This is an alternative way to pass this. Okay, that is a second argument. Then the third argument is size of this messages text. This message structures text RCV messages ith RCV messages text. Size of our ith RCV messages text, and here the address of the ith RCV message. And this is important. This is the exact difference between the previous child and this child. So we need to read in ascending order of the remaining messages. So because of that, I will pass minus 300. So this will ensure that it will be retrieved in ascending order up to 300. 300, and at last IPC, no wait, that means no blocking. Just like before, we will use this one. I'll just copy paste this one to handle an error. This time the variable name is y. That means because this message receive returns -1 in case of an error. So now it is child C2 cannot read from message queue. C2, okay. Even if all of reading is successful, it will only return to here. Then we will print child C2 read from queue successfully. Then we have to print the read messages in order, like before. Printf child C2, and we have to print the process ID. Person D. So here I will use the get PID to retrieve this one, process ID, and read messages are those 4 messages which were read. Perspective. And the first argument is, so this one is get process ID. And this string is nothing but receive messages first index, that is RCV messages 0. And that one's not all the members, that one's text. RCV messages 0 dot text. Then RCV messages 1 dot text. Then RCV messages 2 dot text. And at last RCV messages 3 dot text. Right, so this will print that it is child C2 with process ID and print all the red messages. And after that, it should exit with an exit message. Printf child C2 exiting, and it will exit. So once this child C2 is exit, then child C1 is waiting until child C2 is exiting, then it will also exit. Once it exits, the parent process P1, after sending all the messages to the queue, is waiting until the child C1 is exit. So after child C1 is exit, it will read the remaining message and exit. So this is the whole program which is used for interprocess communication between three processes. So there is interprocess communication with three processes. This is how you can use message queues for enabling interprocess communication. So in this example, only one process created the message queue, but still the other processes could be able to access it and receive and send messages to the queue. Receive and the other process can send and receive messages to the queue, enabling inter-process communication. So we will see whether this works or not. Okay, successfully compiled. This file exists. Okay, we forgot one thing. So once all the processes have finished creating the message queue, we should delete the message queue. So this parent process is the one which will be exiting at last, So we will delete the message queue before the parent process exit. So how a message queue is deleted, we discussed that one in last week. That is done using the message control function, msgctl. This function, it is used to control the function of message queue. You can read what is inside the message queue, the statistics of the message queue, data structure, or write into the message queue data structure using this one. Other than that, what we are interested is in this message control is to delete a message queue. So the first argument is the message queue identifier. The second argument is the command. So for the command, there are a set of commands. So you can even use IPC remove ID, IPC step, and IPC set. So this will retrieve the status and this will set. That means this will read from the message queue to the message queue structure defined outside, or IPC set will read from the message queue structure defined pointed by here outside and set those values into the message queue structure identified by this. So we are not interested in those operations, but what we are interested in is deleting. So if you specify IPC remove ID as the command and not specify any message queue ID data structure here, if you don't specify any message queue ID data structure, that is, you specify this one as null and command as IPC remove ID and pass the message queue identifier here, then it will remove the message queue. So we will use that term msgctl message control. The message queue identifier is message queue ID. Message queue ID. Then the second argument is, that means the command cmd is IPC remove ID. IPC remove ID. IPC remove ID. Then at last, we are not specifying any message queue data structure, so this one will be null. This one will be null. So this will remove.